Okay, welcome GenBio 2 to our first of many mini online lecture videos that I'm going to post and share with you all to help us make it through this quarantine together. I am recording this in my kitchen at my house, well, in my dining room at my house. The audio probably isn't going to be great, and also if you hear crying in the background, it's probably my cat that's mad at me for not paying attention to her. Just in case she decides to interrupt. I also live near a bridge, so you might hear traffic in the background. Hopefully, this will go okay. So, where we left off before we were rudely interrupted by coronavirus is we were talking about trying to package, no pun intended, all of this information about transcription and translation into one whole idea, and by comparing and contrasting prokaryotic versus eukaryotic gene expression. And we were going through a list of 5 major differences between gene expression in prokaryotes and eukaryotes. The first one that we talked about was that prokaryotes take it easy and they don't have any introns. You can see the introns here in the eukaryote. And so there's nothing that they have to cut out before they make their mRNA. So they just copy it straight or transcribe it straight into mRNA. And that was my phone. Sorry about that. I will mute my phone next time. Okay, so major difference number 1. Prokaryotes, no introns. Eukaryotes, they got introns. Okay, the second difference that we were talking about is that in prokaryotes, several genes can be transcribed into a single mRNA molecule. But in eukaryotes, you only got one gene per mRNA molecule. And so in that way, eukaryotes are keeping it simple. So difference number 1, prokaryotes don't have introns. Difference number 2, prokaryotes can make many genes from a single mRNA molecule. Difference number 3 is that prokaryotes don't have a nucleus. Hopefully you already remembered that. Eukaryotes do have a nucleus. So what that means is that transcription and translation are coupled in prokaryotes. Nothing's got to travel in and out of a nucleus. And then in eukaryotes, you got transcription happening in the nucleus, and the mRNA is transported to the cytoplasm for translation, as you can see here in this picture. So that's difference number 3. Difference number 4 is that prokaryotes don't have a 5' cap, a methylated GTP that they add onto, or that they use to recognize during translation. So to start translation in eukaryotes, they start at that AUG codon, but that codon also has a 5' cap that binds the ribosome. Prokaryotes, they don't got that. No 5' cap. That helps start translation. So that's difference number 4. The 5th difference is that prokaryotes don't modify mRNA after transcription. Translation is going to begin before transcription is completed. And again, transcription and translation are coupled in prokaryotes. But in eukaryotes, as we know, there are a number of modifications while the mRNA is in the nucleus. So you take the introns out, the exons are all spliced together, you got to add that 5' cap, and then you also got that poly A tail that's added to, one, the 5' cap is for recognizing by the ribosome, and then that poly A tail, as we talked about, protects it. So those are the 5 main differences. Number 1, prokaryotes don't have introns. Number 2, many genes are encoded in the mRNA of prokaryotes. Prokaryotes don't have a nucleus, and so that changes the location of where all this is happening. There's no 5' cap that's recognized at the initiation of translation in prokaryotes. And then there's no modification of mRNA after transcription by prokaryotes. So those are the main differences that we have. And while you're trying to put all of this information together on transcription and translation, this picture right here I think illustrates really well how you go from a chromosome to transcription to translation to create proteins. And now to bring it back to some stuff we've talked about earlier on in the semester, let's talk about sickle cell anemia, Once again, I know you're probably sick of hearing about sickle cell, but we're going to bring it up again. So there's only a single base pair change mutation that is present in sickle cell anemia versus normal hemoglobin sequences. And that single base pair difference changes the amino acid, and then that changes the shape of the hemoglobin molecule, and then that change in the shape of the hemoglobin molecule, the protein, is what changes the shape of the cell. And so it's only a single base pair mutation that changes and creates this disease in humans. And so that finishes up for what we're going to talk about for transcription and translation. Next video is going to be on photosynthesis, but photosynthesis is not going to be on the quiz this Friday. So tune in next time for photosynthesis. Bye-bye.